Good day. So in this video, I'm going to show you how to run linear regression models using STATA. Of course, we have done that in our previous video, but in this episode, I'm going to show you how to include special functional forms in your regression models, how to extract those models, how to extract the results of those models, particularly their um, marginal effects. I'm also going to show you how to compute for some post estimation statistics after running those regressions. And towards the end of the video, I'm going to show you how to export those results in either Excel or MS Word for presentation purposes. All right, so let's start off by setting our directory as usual. So it's already preset here. So I'm just going to run this, right, just to make sure that State already recognizes the directory. So let's run a sample. Let's run a simple model using the wage data from Wooldridge. So let's type use wage1.bta clear. Right. Of course, there's no data set loaded in the system, but just to be sure, right? So we have this data. It's really a nice data. It's a really nice data set because it includes dummy variables that we can uh, include later in our regression model. Right. Now, some people would normally just include them as it is, but it adds a little bit of complication, especially if the categorical data is not coded as 0 or 1, right? So that's going to result in, that may result in inconsistent estimates or inconsistent coefficient results, right? So let's try to run a simple log of wage model. So basically wage elasticity model. So suppose you wanted to, we have done this in our previous video, but suppose you're asked to include, say, the quadratic or presume that, say, experience has a quadratic effect or a quadratic relationship with the elasticity of wage, right? Meaning, as experience increases, of course, your wage also increases, but the additional increase in wage becomes smaller and smaller. So you have a diminishing effect on work experience. How would you include that? How would you set up your model to capture that relationship? So there are two ways. You can either just type log of wage, right? Let's try to control for education, and let's add experience. So some people just generate experience squared. So you can type in generate experience squared. So you would create an experience, a squared experience term, right? And you'll include that in the regression model. That's fine. That's perfectly fine. However, you're missing out in terms of computing for the actual marginal effect of experience if you're just going to include that as a squared term. Right? So here we're going to utilize the margins command. We're going to utilize the margins command to measure precisely what the marginal effect of experience is. And we can see that by setting it, and it's fairly more flexible and it's easier to use because it allows us to substitute reasonable values for experience, right? That will allow us to measure the actual marginal effect. Right? So how do we include a how would you include a quadratic function or a quadratic form for experience in your regression model without creating that experience squared variable? So let's note it here as including a quadratic term in your regression. So suppose you wanted to include experience, a quadratic term for experience, right? So to do so, I'll use the pound sign, double pound sign. Okay. So here, when you include a double pound sign, some millennials will call it a hashtag. If you include a double hashtag sign in your variable, between your variables, you're telling Stata that you're including a quadratic term for experience. The C here indicates or tells Stata that experience is a continuous variable and you wanted to include a squared term, its level plus its squared term in your regression model. So if I run this, right, it instantly includes the level variable for experience and the quadratic term for experience. All right. So here's the result. All right. Here's the result. Now, the thing here is that, as you can see in the model, the results show you that experience is indeed, or experience has a positive, significant relationship with log of wage. But increases, as experience increases, its impact sort of diminishes over the years, right? So as you include more years, right, the additional wage, the marginal increase in wage also diminishes. And in fact, if you try to plot that, we'll do that in a separate video. But if you try to plot that relationship, you would see that it's indeed a quadratic fit, right? You're going to see a quadratic fit between log of wage and experience, right? Now, the next question is, and as you normally see in your econometrics textbooks, what then is the actual marginal effect of experience? Is it 0.04? And of course not, right? If you just say that it's 0.04, you're basically assuming that there is no quadratic effect. And it seems that experience has a constant positive marginal effect on log of wage, which is not the case, because we have seen here that experience is significant. The quadratic term for experience is significant. Right? Significant. So how then do we measure the actual marginal effect of experience on log of wage? So we can use what we call the margins command. So this allows us to compute for the marginal effect of experience. Right? So to do that, we'll just type margins, comma, dy dx, right? Dy dx. If it is a constant, if you just have a level variable like education, you would still see, you will just see 0.09 after running margins, right? But here, right, since experience is a quadratic term, and since experience is a quadratic term, STATA recognizes that. And if we run this, it will give you the marginal effect of experience. Take note that we're trying to sort of compute it. Let's explicitly run the formula here. Take note that we're trying to compute for this. You're looking for 0.04. Basically, you're looking for this computation. You can manually do this to verify, but of course, that's going to be tedious, especially if you have so many variables to consider. So what margins compute is literally this. So you have 0.04 minus 2 times 0.007 approximately times experience. So basically, we're sort of assuming a value for experience here. And normally, when you type margins and say dy, you take the marginal effect of experience, marginal effect of one variable, STATA assumes, or STATA fits, or STATA plugs in the mean, or sample mean of experience. We can verify that, right? So 0.16 basically is what we're seeing here is that the marginal effect, the marginal increase in log of wage, marginal increase in wage, let's be more specific, the marginal increase in wage at the average years of experience, is around 1.67%, right? Let's try to do that. So first, let's try to get what's the mean of experience first. Right, so it's 0.17. So if I try to say compute for that, so roughly you have 0.04 minus 2 times 17.02 times 0.0007, and you will get the same result. Right, you get the same result. So basically, what margins does is it computes for the marginal effect of a quadratic term and assumes, by default, it assumes the mean of the independent variable that you're trying to examine. Now, the good thing about margins is that you can preset the values for experience. So say you wanted to get the margins or the marginal effect at specific values, right? And that's the nice thing about margins, no? If you just included a generic quadratic term in the regression analysis, you cannot do this, and you can do this, but you'll have to do it manually. So say for instance, we wanted to get the marginal effect at specific values. Let's say 5, 10. We already know the mean. Let's just include it, 17 and say 20. So type margins dy dx, right? Experience at 5, right? Let's try at experience 5. Okay. 10. Let's see if it runs. So you add it separately. Okay. At 5, you have 10, 17, and 20. And here is the result. So it tells you that for 5 years, at 5 years of work experience, the marginal effect on wage is around 3.3% or 3.4%. Right? Now, as the years of experience increase, as the number of years increases, right, the marginal effect sort of diminishes, right? So from around 3.4% down to 1.2%. So that's the nice thing. That's the nice thing about margins that you can't normally do if you just include the variable as it is in your regression analysis. Right? For further assistance, you can just type help margins to give you a more detailed discussion and more comprehensive list of syntax that you can include in the margins command. And margins basically when you do nonlinear regression models, the margins command is particularly helpful. It allows us to compute for marginal effects for nonlinear models. Okay, so that's for inclusion of a quadratic term. Now, in the regression analysis, you'll also ask you may be asked to include an interaction term, between two continuous variables. So let's say you have a reason to believe that education or the marginal effect of education is tied with experience. Right? So it means that, the effect of education is not constant, but rather it's dependent on the level of experience that one has, or vice versa. The effect of experience may depend on the years of education that a person has. Right? So if that's the case, let's try to run an interaction model. So you're going to do this if you have a reason to believe that, say, experience depends, it's not a constant, the marginal effect of experience is not constant, but rather depends on another variable, let's say education. So to do that, you have regress L wage. Okay. Now, we're going to leave it as it is. You can specify it in two ways. You can say, if you're more comfortable doing this, you can just type educ experience and the quadratic term, or sorry, the interaction term, which is denoted by educ single pound sign to indicate that it's just a product of two terms and you're not including the levels. Or you can do it this way. Regress L wage, C educ, it's shorter, C experience. So basically the same. Okay. So let's try to run this and see to verify that they're indeed the same. See, it's identical. It's practically identical. Okay. You're getting identical results. Right? Now, the thing about interaction terms is that, again, like in the case of the quadratic term, you cannot get the marginal effect in a rather straightforward way, right? You still need to make some assumptions about the level of education experience that you wanted to consider. Now, normally you would use the mean, right? And if you're comfortable assuming mean values for, say, education and experience, setting it as holding it constant, and you wanted to base your marginal effects on that number and that value, that's fine, right? So say you wanted to get the marginal for edu, right? So you just type margins dy dx edu experience. You can do a list. You can type a list. Okay? And it now gives you the marginal effect. So here what we're seeing is that the marginal effect of education on log of wage, assuming mean values for experience, its co-interaction term, right? Co-interacted term experience is around 9.9%. On the other hand, right, the marginal effect of experience holding education constant in at its average value, right, assuming average years of education, the marginal effect of experience is around 1.01%. Okay, so that's the thing. However, of course, you have to be careful, right? We're just doing this for demonstration purposes, but you have to be careful in interpreting these numbers, because as you can see, the interaction term between education and experience is not statistically significant. Meaning this is practically zero. At the population level, this is practically zero, and you can just drop it from the regression analysis because it will just generate noise, right? Or you can also say that probably this is highly collinear with your level variables. Okay. So that's for the interaction term. Now, interaction terms also work when you have a dummy variable. So before we do the interaction term for dummy variables, let me show you first how to include dummy variables in the regression. Right? So adding dummy or categorical values in the regression. How to add dummy or categorical variables in the regression. So you just type regress. Say, for instance, you have a reason to believe that there is a wage differential between males and females. So let's add the female dummy variable here. So let's try to control for educ. Experience squared is, the quadratic term for experience is significant. So we'll just type experience. Now, how do we add the dummy variables? Now, here's the key, right? Sometimes you're not sure what the coding of the variable is, right? You're not sure about the coding of the variable. Of course, you'll have to check that before including that in the regression model. But if you're unsure, right? And just for precision, for the sake of precision, when you want to include the dummy variable in your regression model, you'll need to use a factor function, right? Consider it as a factor. So when you want to include a variable, when you want to include the factor variable, a dummy variable in your regression model, just type I, female. So that I here, that I dot function here represents a factor variable. So you're basically telling STATA that female is a factor / categorical / dummy variable, right? And STATA has to treat it as such, right? When you don't include I dot, STATA will practically treat this female as a continuous variable, and you cannot use that. You cannot use the advanced functionalities of margins when you don't include this factor variable. This will come in handy. This will come in handy when we want to get the margins for, or say, the discrete changes in the dependent variable when you type in margins. So let's run this. All right. So the factor variable is significant. So your dummy variable significant tells you that females tend to earn about 50% less, and about 50% less than males. Right? So males earn higher, at least for this particular data set. So how then do we use the margins? How to compute margins for dummy variables? Here's the thing about dummy variables. Here's a really nice thing about dummy variables. you can do the interpretation two ways. Number one, you can get the discrete change. You can get the discrete change in, sorry, let me rerun this model again. So this is LOH. Yeah, so that's much better. I'm sorry about the previous model. So that's much better. So it tells us that females tend to earn 34% lower than males. So that makes more sense. So, now, how do we compute margins for dummy variables? Now, here's the nice thing about margins and dummy variables. So you can do you can run two kinds of interpretations, right, or analysis. It's either you can either get the marginal or discrete change in the dependent variable, which is done by dy dx, or you can measure, or you can get the change in the predicted value of the dependent variable, right? Predicted value of the dependent variable across two groups, i.e. male and female. So let's do the first one first. Let's do the first type of analysis. So, which is the discrete change in LOH. So to compute for the discrete change in LOH, we'll just type margins dy dx female. Or to be specific, let's type 1 female. Okay. So STATA notes that dy dx is discrete change from the base level. So discrete change from male to female. So it means that wages are lower, assuming that the rest of the variables hold their actual values, right? So this is the average. This is going to be the average decline or the average difference in wages between males and females. Now, what if you wanted to get predicted LOH across groups? Now, if you wanted to get the predicted log of wage across groups, you'll just have to type margins female. Right? You type margins female, and holding everything else constant, education constant, experience constant. This will now show you the difference in wages, or sorry, it will now show you the predicted wages between males, which is category 0, and females, which is 1.44. Of course, this is in log terms, so you'll need to convert that in level terms. So you'll just need to use this as an exponent for the natural number e. All right, so that's your margins. That's your margin. You compute margins. You can compute the discrete changes. It's really neat. You can compute for the discrete change in LOH, and you can also get the predicted LOH across groups. Okay. Now, next, what if you wanted to interact this, right? What if you wanted to interact female with education, right? So what if you have a sufficient reason to believe that education is influenced, right? Basically the marginal change in education is dependent on whether the respondent is male or female. Right? So if you interact that, so we'll have regress LOH. So this is a factor and continuous variable interaction. So this is going to be I female, C edu. So notice the difference, right? So you're telling STATA to include a level, the standalone variable for female. You're telling STATA to include a standalone variable for education, and you're telling STATA to include, because of the double pound sign, you're asking STATA to include an interaction term between female and education. So let's still include experience squared. And let's run this. So you're just setting in this particular specification, you're just setting that the education, the marginal effect of education depends on whether the respondent is male or female. Well, as it is, it looks like it doesn't. Right? Education doesn't really depend on female. So the marginal effect of education is the same across two groups, right? Across two groups. But what if this is not, what if this is statistically significant? How will you interpret these results, right? So you can still use margins to compute for marginal effect education. So if you wanted to compute the marginal effect of education while accounting for this supposed difference across groups, so you just have to type margins dy dx edu. Right? That's the average, right? So well, if everyone's, but doesn't really make sense. So let's type by female. Or over, actually. Okay, that's the same. By and over female is the same. So what we're computing here is the marginal change, right? We're looking at the marginal change, the marginal effect of education on L wage while controlling for the two groups, right? Female or male. So as you can see, the marginal effect doesn't really differ, right? Which kind of supports our regression results here, right? The interaction term between female education is not statistically significant, which indicates that education, the marginal effect of education is constant between two groups, between male and female, and rightfully so. It's around 0.08, right? 0.08 between two groups. So it's not really different. It's not really different. So you have a sort of constant marginal effect of education, right? So you can see here between the two groups. Okay. So that's how you compute. That's how you compute for the marginal effects, right? Marginal effects with the inclusion of interaction terms. Now, how about for the case of say the dummy variable? So what if I wanted to get the margins or the discrete change in female, knowing that it's interacted with education? So you can just do this, and STATA will just assume that you're using the actual levels of education, and that's your average change. If you wanted to get a specific value for educ, say average educ, right? So it's roughly the same. So you're getting the mean. You're at mean years of education. This is the marginal effect of female. Right? This is the marginal effect, or the discrete change. Sorry, the discrete change of being a female from moving from one group to another in terms of wages. Okay, so this sort of summarizes the things that you can do with interaction terms, factor variables, interaction terms, and computing for marginal effects in STATA. Now, what if you're, well, for model specification checks, right? For consistency checks, what if you wanted to get either the predicted values or residuals, or maybe for plotting purposes, you want to get the predicted values or residuals of your model? So it's very simple. It's very simple. So if you wanted to get, say, the residual of the residuals of the regression, right? Just have to type predict, and you set the variable name for the residual. Let's say you had receipt. Then you just type this. And if you notice, in your variables manager, you now have your residuals. Right? Now, what if you wanted to get the predicted values or the fitted values? Right? You just type predict, and you set the variable for variable name for those fitted values, and that's going to be predict y hat. Right? So those are your fitted values. Of course, depends on your purpose. You can use your U hat to test for heteroscedasticity. You can also use Y hat for plotting, right? Or maybe you wanted to generate some predictions. You wanted to generate some predictions from your models. Okay. Right. So much for the basic functionalities of STATA. Now, here's a really interesting question that usually arises when it comes to regression results, right? Some students or some users of STATA who don't have this program who don't have this command that I will show you, normally they will just copy and paste it on the fly, right? And more insultingly, some students will just snip the STATA results window and include them in their manuscripts or in their draft papers. Of course, that's really annoying, right? And it will become impractical. Copy and pasting the results from the command window becomes impractical when you're running several models all at once. Okay. Now let's suppose we have that scenario. Right? Suppose that we have that scenario that we are required to run several models, and you wanted to present that in a regression table. Okay. Of course, you cannot do that copy paste thing anymore. Okay. So suppose you wanted to run several models in one go. And you wanted, of course, to display that in a results table. So let's set up the models first. Let's say you wanted to generate the output for this one, for all of these models in a single table. So what I would normally do is set up a global macro. I'll set up a global macro, say global M1, that will sort of automate the process of running the regression. So we only have a single dependent variable, so that's not an issue. The case here is that we have several combinations for the independent variables, right? We have different specifications for log of wage. So we first did something like education and the quadratic term for experience. That's our first model. Our second model is educ and sorry, educ and experience. Our third model is educ, experience, and female. Right. And our fourth model, or fourth specification, is the interaction term between female and educ and experience. Right. So let's name that macro model 4. Right. In actual practice, this can run up to 12, 15, 18 models at a time, right? You have the same base specification. In our case, our base specification is education and experience, and we're just adding some controls, some additional controls in the process, right? Of course, you can run several regression equations all at once, but it becomes unwieldy, right? It becomes unwieldy when you have several models that you wanted to run, and basically you just have the same dependent variable that you're measuring, right? Now, to automate the process of estimating this, to automate the process of estimating these different specifications, I would normally use what we call the for each, or let's just say for values. Either for each or for values, right? So STATA has a way of looping things, a way of automating things. So notice here that instead of running several specifications, the macro will just allow me these macros. Instead of specifying the actual variables, I can now just run across these set of numbers from 1 to 4. So if I wanted to estimate all of these models, I will just tell STATA that I will just tell STATA to run the numbers from 1 to 4, right? For all of the values 1 to 4, so models 1 to 4, I want STATA to regress L wage on the particular model So the dollar sign here is the way to call. This is basically how you call for the macro. Call for the global macro. You use the dollar sign. So let me pause here for a moment and describe what is going on. So you're basically telling STATA to run across a list from 1 to 4, right? So for each of those values I equals 1 to 4, and you're telling STATA to regress regress LWH on the particular specified model. In this case, if you start at 1, this becomes you're basically running regressing LWH on model 1, which is educ and experience squared. For M2, right, it will step right again, right? It will move to the second number, down to 3 and down to 4. So it sort of repeats. It repeats this line from 1 to 4. So from model 1 to model 4, and that's captured by I here. Okay. So it repeats the process, right, across 1 to 4. And our stub or our indicator function is our indicator variable is I. Now, how will you save? How then can you save these results? How can you save these results in one table? So we have this, or I have this special command that you can install, right? You can install in your machines. You have what we call out reg2. You have what we call out reg2. Okay. So outreg2 exports the regression results in a nice table. It exports in a nice table. So what I will do here is just type outreg2 using, so you just specify what Excel file, you just specify the Excel file that you're trying to use, or where you want to save your results. So sample, say you have sample results, XLS. It doesn't use a modern format for Excel yet. You can just specify here Excel, right? Let's specify the column titles. So you can specify the column title. So here, I'll just type MI. You're basically telling STATA to name the columns depending on which model you're trying to run. Okay. You can also include the adjusted R squared. By default, it doesn't include the adjusted R squared, but if you wanted to include the adjusted R squared, you can just say add stat adjusted R squared, and you type E R2. Okay, and you type the option append, right? You're basically appending columns. You're appending columns 1 to 4. Okay, so let's try to run this. Okay. So in summary, what we're doing here is we're automating the process by setting the specification right ahead of time, storing them in a global macro. So macro 1, model 2, model 3, model 4, and automate the process of estimating all of these models by using forvalues, right? So it's telling STATA to run across a list of values from 1 to 4, right? I is basically your catch. I basically captures that 1 to 4, that list from 1 to 4, and then you'll run the regression. Basically, you're basically repeating the regression line from 1 to 4, for models 1 to 4. So let me run this. So that automates the process, right? So it runs the regression. It runs the regression, right? You cannot copy paste that. Of course, you can. I did that before. You can do that, but of course, it's really tedious. It's really tedious, right? So it automates the process for you, and at the same time, because of the outreg command, right? Because of the outreg command, you can now check you now have your sample results here in an Excel table. So just ignore that usual error, right? And it now shows you the results, right? So you don't have to copy paste anymore. Your levels of significance are already set by default, right? You also have your standard errors. These standard errors are difficult to copy in Excel, but because of the outreg command, it allows you to export those results on the fly. You'll just have to reformat your columns, your variable names, of course, but that's easier. That's practically easier than copying the results from your results window. Okay. So that concludes our video presentation for today. And in our next video, I'm going to show you more of the tricks, right? More tricks, more models, more model specifications using STATA.